Today we're going to take a look at some of these radioactive particles that we'll be looking at over the next couple of days. And the first one we're going to look at is the alpha particle. An alpha particle can actually be demonstrated several ways. The most common way that we're going to see it set up is as a helium isotope. So when we're looking at these nuclear reactions, we're literally going to see it listed like this. It can also be represented with a Greek symbol alpha that looks somewhat like a fish. Key things to understand about an alpha particle is that it is extremely heavy. It is the heaviest of the radioactive particles. And it's heavy because we see that it actually has 4 particles in its nucleus. It also has a positive 2 charge. Because that alpha particle is so heavy that it can easily be stopped. We are constantly being exposed to alpha particles throughout the day, and they're just very heavy, and our skin actually protects us. So something as simple as our skin or a piece of paper can block these alpha particles so that they can't penetrate through things. The second particle that we'll be looking at is a beta particle, and a beta particle is simply a fast-moving electron. And so we'll see beta particles represented a couple of different ways. You will sometimes see them represented with a capital B. But since a beta particle is a negatively charged electron, we understand that it has 0 mass. We understand that the charge on it is a -1. So occasionally you'll see it represented like that in an equation. Occasionally you might see it represented as an E for an electron. Again, couple key things to remember: that a beta particle is an electron, and we'll talk about how that happens later on in today's lesson. Another thing to remember, because it has no mass, it is able to move a lot faster. Therefore, you're going to have to look at some denser metals like aluminum in order to stop these beta particles from penetrating various things. This last, I'm hesitant to call a particle. It's more a form of radiation, and that is gamma. Gamma has no mass, and it has no charge, and we represent it with the Greek symbol gamma. These guys are more thought of as like a form of energy almost, and they can very easily penetrate through our skin, our clothing, things like that, and so they tend to be more dangerous to us. Gamma particles can be stopped with lead and concrete. So when we start studying some of these nuclear disasters that have occurred, Russia in particularly tried to use concrete to stop some of that gamma decay, but even we understand now that lead and concrete can slow them down. It doesn't always stop those radioactive particles. So key takeaways to begin with are these 3 particles and what they look like in a nuclear reaction. One of the ones that we haven't looked at because it's not a radioactive particle necessarily, but it is going to show up in some of our equations that we look at today, and that's a neutron. When we're representing a neutron, we understand that a neutron has a mass of 1 AMU, and it has no charge, and we would simply represent it with an N. So let's go back over this. Here we see that is definitely a neutron. We know that an alpha particle is actually just a helium isotope. Okay, that's the alpha. We understand that a beta particle has no mass because it's an electron, has a -1 charge, and again, we can represent that with that capital B for beta, or you could also see it written as a lowercase e for an electron. And the last would be that gamma looking like that. No mass, no charge. Really just a form of energy radiation. Okay, now what I'd like to do is we've taken a look at those couple different particles. Let's look at a nuclear reaction. We have an isotope of potassium, and I know it's potassium because capital K there. Hopefully now you're saying, oh, that's that helium particle she was talking about, or alpha particle, I should say. So when I'm talking about a nuclear reaction, this is what I'm talking about. And nuclear reactions will stand out to us because they're written with a lot of isotopes. And so let's just kind of talk through what we see here. We see that we have an isotope of potassium, and it is breaking down. And we know it's breaking down because here we see that arrow. And what's it breaking down into? An alpha particle. and a chlorine isotope. You're going to hear this that we started with is going to be referred to as the parent nuclide. And that's because that's what we started with. Once that parent breaks down, this over here is called our daughter nuclide because it is what is produced through this process of decay. And then, of course, right here, we know that that is an alpha particle. Therefore, we would call this entire process alpha decay. And think about what that word decay means. Decay means to give off. And that's what's happening here. This isotope, this potassium, is giving off an alpha particle, which is right there. And what is left over is that chlorine isotope. So that's just a simple introduction to some of the vocabulary terms that we're going to be using over these next couple days. The next video will show how to balance one of these nuclear reactions.